And here is progress, yeah. So it's meant to be a fairly extended program, which will eventually have specific applications. I mean, it already has applications, including what we've written. So motivation, there is twofold motivation. So there is this Gramov's paper in '85 and Donaldson, yes, like '95. And what they do, they bring algebraic geometry into symplectic topology. And this has had many applications. And on the other side, there's also motivation from algebraic geometry, mirror symmetry. And that's the Gross-Seibert. The Gross-Seibert program for a fairly direct proof of mirror symmetry. So more specifically, this goes back to a question in Gramov's '86 book, and he asked, is it possible to define symplectic varieties or subvarieties? So this is, of course, very standard thing in algebraic geometry, and he suggested doing the same in symplectic topology. And the second one is he asked for a multifold symplectic sum construction. So the standard one is twofold. That comes from the paper of Gumpf. So what this should do, you've got a bunch of symplectic manifolds. With some conditions. And out of this, you should make another manifold in a nice way. Now, so Gross-Seibert program actually suggests that this may not be the right formulation of a question. So it actually suggests that maybe 1 should be replaced by 1 prime, and that would be varieties with log structures. So symplectic varieties with log structures. Actually, more precisely, nice log structures. Now, what nice is keeps on changing, right? In algebraic geometry, or in the Gross-Seibert program. So, but certainly the most basic example is normal crossing singularities. So normal crossings. Subvarieties and degenerations. So especially divisors. As subvarieties. So what it means to be log normal crossings that locally, normal crossing degeneration, that locally we have some space that looks like Z1 up to Zn lambda. This is NC cross Cn. So normal crossings means that we're just taking, we take a product of this. So special case occurs when lambda is 0, and then it's singular. So cross something else, because the other part could be smooth, and this contains Z0, which is to say lambda is 0, which is well, basically Z1 up to Zn, and Cn actually this is 0. So this is the union of coordinate hyperplanes. So Zi equals to 0. It's the union of coordinate hyperplanes in Cn. So this is a degeneration in the sense that you can project this down to C. We go lambda to lambda. And this is over 0. So you have a smooth Z lambda for lambda not equal to 0, lambda in C star. And this degenerates to normal crossings Z0. So this is normal crossings variety. This precisely means that it's a union of these things, locally in this form. And this Z0 inside of Z is an example of normal crossings divisor, which again just means that locally it looks like that in here. Right, so these pictures are not always easy to draw, but it's easy to draw this in case n equals to 2. So here we have Z lambda, and we can think of it as being some manifold X, and when Z0 this looks like this. It's like X1 and X2, and here we have what I would call X1, X2, the intersection. And so this is essentially C cross C2, 1 cross CK, C2, 2 cross CK, and that one is just 0 cross CK. So this Z0 is X1 union X2. So this thing sits in both parts, and we take the union. So this is just smooth varieties identified along a smooth divisor. And you can think of this makes perfect sense symplectically, this part. so n equals to 3. Also, in this case, I will have to draw a 3 or 4-dimensional picture. So I'm only going to draw Z0. So one should think of each of these as being coordinate hyperplane. So this is one of coordinate hyperplanes. Then this one, x1, 2, well, this is C3, 1, 2 cross CK. So the cross part does not really matter. So this is just Z axis, Z3 axis in this notation. So this is x2, 3. So what we see here is that Z0 equals to x1 union x2 union x3. And that's again smooth varieties. But now identified along NC normal crossings divisors. And these divisors are x1 union x1 free inside of x1. So both of these she's in here. x1 2 union x2 3 and x2 and x1 3 union x2 3 and x3. So you identify like this in obvious way. So already these identifications are not so simple, because at this point you identified 3 things, here you only identified 2. So what is needed for Gross-Seibert program? So the first thing is GWs of this NC variety Z0. So of course you could just take this variety, you could just say it's 0 and that's invariance, but that's not very interesting. So this is single variety, so a priori it's a question of how you define this with Gromov-Witten invariance. And the way it should be defined is with somehow the equivalent to Gromov-Witten invariance of a smooth fiber in some sense. And the second thing is GWs of Z0. It would be nice to split them into GWs of xi relative to and relative to NC divisor. So I'm going to call it VI, which is union over J, not equals to I. So you take all the pieces that sit inside of xi and form the normal crossing divisor. And so ideally you'd like to define Gromov-Witten invariance with xi with respect to that, and those relative Gromov-Witten invariance should see the absolute ones here. So n equals to 2 case is, so in this case, so this is this picture, that picture. So this is completely standard and almost historic. So for n equals to 3, so the first part, this kind of Gromov-Witten invariance, it's in algebraic geometry, it's essentially done in some way with Abramovich, Chen, and Gross-Siebert 5 years ago. So this is in algebraic geometry. So 2 is more interesting. So Brett Parker claims he can do it. So the trouble is that he cannot really explain what the formula is in a way which, in a standard way, let's say. So that one can actually use it. So this is in his exploded category. And so one way to, so exploded category is not exactly almost scalar, but it's pretty close. It's not symplectic. And the thing about Gromov-Witten invariants, that they're fundamentally symplectic invariants. So if this is supposed to work, it should work symplectically. And in fact, if it does work symplectically, it might be easier to establish things, because that's more, you have it's softer, so you have more flexibility. So symplectic perspective.
May I ask a question?
Yeah.
So, I mean, on the face of it, for Gross-Siebert, you need an additional step. So, depending on how you want to think of it, I mean, do you have in mind that you would first sort of resolve the singularities in the log structure so as to get to a normal crossing situation?
Well, so that would be one approach. I mean, I ideally would like to actually extend our results. So we have defined the notions for normal crossing singularities. So ideally, we would like to define symplectic notions for nice log structures. Now, what nice means, some kind of toric thing. So ideally, we would like to actually generalize the main results. So without resolving. And that would actually be a step one could do sooner, because it's still on the level of symplectic topology. So the talk I'm giving today is not really on the level of Gromov-Witten theory, it's on the more basic level of symplectic topology. It's in a sense like giving a talk about logarithmic structures and forgetting all this Gromov-Witten theory stuff. So the symplectic perspective, so in n equals to 2 case, there's a symplectic sum which is Gampf so 20 years ago, but it was actually suggested by Gromov in his book. So what you have here is you have x12, which is symplectic divisor, a smooth symplectic divisor. And then if you have if the normal bundles of these things are dual, so if the normal bundle of this one in the two things is dual, then you actually get symplectic vibration z omega z over, so I'll say over C, is actually over a small disk, but it doesn't matter. And the central fiber of this Z0 is precisely the union of the two things. Other fibers Z lambda. So what people usually call symplectic sum is actually the smooth fibers of this thing. So it's different manifolds, but they're all equivalent up to symplectic deformation equivalence. So there is a slightly later work by Symington but this is only dimension 4. So in this case, it's really fairly topological. There's not much structure. And so she can do threefold sum. And she can also do what she calls n-fold sums. But this n-fold not with Gromov moment. You cannot possibly, the way he meant it, you cannot possibly have a fourfold sum in dimension 2. You have to go to dimension 3 at least, because you have to have these configurations. So this is kind of background part a little bit. Any questions? So the situation remains that one still has to define a symplectic notion of normal cosine divisor. So we have this X, which is a manifold. V and X is subspace. So what I want locally is that this V equals to the union of VI, only locally, where each, so the I in X is smooth of real codimension 2, so that it can be a symplectic divisor, and the I's intersect transversally. So the picture is then this. So we've got V1, we've got V2. So this I would call V1, V2, where we intersect, and this is a smooth manifold. And what I'm going to define is sim plus of xv. So this is how we wrote in the first version of the paper with a plus. Maybe a better notation would be to drop a plus. So the reason for not being sure which is better is the following. So this should be omega on x, such that that all vi and the intersections are symplectic. So this should be symplectic submanifold. So all this should be symplectic. So it kind of makes sense. It seems to make sense to just call this stuff without the plus, because it is a symplectic form. But now comes the second condition, which is motivation for the plus, is that if you look at the symplectic orientation on V1 intersect VIK, so symplectic means this is from omega n minus k. This should be equal to what we call intersection orientation from x V1 up to VI1 VIK. Now, so if you only take if you take a single VI, the symplectic orientation is by definition the orientation here. But so each of these is oriented by symplectic form. So if you intersect two of them, the intersection is also oriented from here. But a priori, that does not have to be this. Now, in dimension 4, if you have two with symplectically intersecting, this point has to be plus. That's the condition in dimension 4. Now, in higher dimensions, you have a manifold sitting there. And this intersection should be plus 1. And dimension 4, it's pretty easy to see that you can easily make two symplectic manifolds intersect negatively. So this condition is not trivial. So in a sense, the main theorem today is that that's the right notion of a symplectic divisor. So a symplectic divisor would be something where you have x and v and omega like this, satisfying these conditions. Now, so
is this set now empty?
what?
The set symplectic with plus is now empty.
No, this we don't know. So the thing I said x is a manifold. So this is similar to saying you take a manifold and we define a space of symplectic forms on it. It could be empty, could be not. So I think what we're trying to do is symplectic topology. We essentially want to work with components of this space. If it's empty, okay, it's easy. But otherwise, you can do something interesting. So this, there is triples omega rj. So you want to take r to be omega regularization. So what we call omega regularization for xv. And so what this is supposed to do is, you have this picture, and the ideal picture is where is this? Is in a sense this one when you see it in C. Makes everything look like in Cn. So locally it should make it look like this. So you have some neighborhood identifications. And J is a compatible almost C structure. And so the relation with Brad Parker here is that if we look at deformation equivalence class of omega r, that gives Brad Parker's deformation equivalence class of exploded manifolds. So he says you actually need, but our conditions and realizations are too strong for him, but it's still, his deformation equivalence classes have extra additional data. They're not symplectic. And so these are purely symplectic. Well,
the definition of this omega regularization, is that assumed?
So no. So you start with this X and V. So this space could be empty, a priori. A priori, this space could be empty.
What is the space though? Can you makes everything look like CN?
So it means you have a neighborhood identifications. So here, you have a normal bundle here. So this point has a normal bundle. So you can choose a map from a normal bundle. So the normal bundle is split by these ones. So you can choose a map from a normal bundle so that this goes to this one.
Yeah, so it keeps track of the divisors also look standard. That's
Yes, yeah.
Up there, omega lives in sim plus. Omega.
Well, I haven't made a statement yet, but so the point is the only chance for this to happen if omega lives in plus, because this is in CN these intersections are positive, so that's the only chance.
Are these J?
I'm sorry. So compatible, almost C structure are compatible. So what this means is that you have these identifications. So if you take a smooth divisor, there's a tubular neighborhood theorem. And you can use this tubular neighborhood theorem to put a very nice J on it. The one which is, it keeps the divisor almost complex, but it also does not, it has a vanishing, it's essentially integrable in the normal direction to the divisor. So this is the same kind of structure you can put in. So this is what I want in general. So it's a very regular structure, and the reason we want regular structures is to be able to define Gromov-Witten invariants, for example, or to do anything. So the main theorem so if you look at this map from AK, so again, so X is just any manifold and V is some subspace, which locally looks like stratified. So with a projection into, okay, so claim is that the projection goes here. So a priori I didn't say omega was in here, but the projection actually goes in here. So omega Rj goes to omega. So the statement is that this is, so one could say, well, so one statement could be that it's surjective. I mean, there's no chance, because this regularization would require the divisors to be orthogonal. They don't have to be orthogonal. But it is a weak homotopy equivalence. So which means isomorphism null pi k. This is not surjective unless V in X is smooth. So if V in X is smooth, there is a tubular neighborhood theorem. You can always do this. So, but what really matters for application is that in symplectic topology is actually this: the fact that this side is completely symplectic. There is nothing almost scalar in my definition on this side. I just said, intersect positively. It's completely topological. This side has almost scalar stuff in it. And the almost scalar stuff is what you need to do a lot of symplectic topology, because like Gromov-Witten invariance or even symplectic sum. And the point is that, so this is not surjective, but it doesn't matter for applications. So what these applications are most of the time is you take deformation equivalence class in let's say sim plus xv, and you produce something. The something could be a symplectic sum or Gromov-Witten invariance. So Gromov-Witten invariance, like symplectic sum, depend only on the deformation equivalence class. And the way you usually do it, you actually go through these almost scalar structures. It actually factors like this. To define Gromov-Witten invariance, you have to choose an almost complex structure J. To do symplectic sum, you have to choose an almost complex structure J, essentially, or some kind of identifications which is essentially equivalent. So you have to go through this. And for this to work, for this to be well defined, what you really need isomorphism on pi 0. In all the standard cases, this map is surjective. So what you do with Gromov-Witten invariance, you have x omega, you choose a J, and then do Gromov-Witten invariance. But who said that you have to choose a J for every form in deformation equivalence class in here? You can just do it for some omegas. And as long as this is isomorphism pi 0, you're OK. That's the only thing it depends on. And what we have is a big homotopy equivalence. So there's actually far more. So
if I fix a class in sim plus,
yes.
and if I just restrict myself to J's, which make the varieties almost complex,
Yes.
is that space not contractible?
So,
Or compatible? compatible almost complex structures with that sim plus class such that it makes all of the divisors
Well,
almost complex submanifold closed under J.
so essentially, okay, it may be contractible, but you have to comment of one and the other, and we do it via R's regularizations. But the thing is, how can you show a priori that this is even non-empty? So if you just take a smooth symplectic divisor, how do you know that it's non-empty? But besides J, but you want a little bit more. You want 9 Hughes tensor to vanish in the normal direction for all these applications. So how do you know this space is non-empty? Now, the reason you know this, if this is a smooth divisor, there's tubular neighborhood theorem. So what you can do is when you put J on V, and you use the tubular neighborhood theorem to extend it over, and that gives you a very nice J. So this tubular neighborhood theorem is this R. This identification is this regularization. So you actually use the regularization to put a J. So we do the same thing. We produce regularizations, and that allows us to put a J. So essentially, the J is supported on the regularization. But so the reason you're not seeing this in the smooth case, regularizations in the smooth case, because they're automatic. And any two with regularizations in the smooth case are homotopic. So they really don't matter, so you don't see them. And also, in the smooth case, this is surjective, so it seems like it should be surjective, but it doesn't. Okay, so some applications of this. First, so essentially what this theorem is saying, that there exists symplectic topology notions of NC divisor variety degeneration. So I only specified it for a divisor. For variety, you have to have local identifications like this, and it works the same way. Second statement is that each NC symplectic divisor, and you should think of this really as an element of pi 0 of sim plus of xv. So the whole deformation equivalence class. It determines a C line bundle O of xv over x. So when you're doing algebraic geometry, any divisor determines a line bundle, and this happens the same way here. So it depends only on this, up to deformation from one into the other. So it also determines a C vector bundle Tx of minus log v over x. So this part is actually being written now, but so logarithmic tangent bundle is key to defining Gromov-Witten invariants in algebraic geometry, because this is what gives you this is the log structure. So each NC symplectic variety x determines what we call OX O partial X. So what this thing is, this is the single locus. The single locus of X. So the single locus is precisely where you don't have the smooth parts. So here, the single locus here is this point. The rest is smooth. In this case, the single locus is this union. So this is what we call normal bundle. To X partial in X. So it's a line bundle.
What is this line bundle in the case of two transversely intersecting C's?
It's a product of two so O of x1 x2 x So the product is over C. The complex structure is defined by the deformation equivalence class.
Is the line bundle M3 the restriction of the one M2?
What?
Is the line bundle over X delta the restriction of the one over X?
No. So in this case, yes. I mean, so there is a relationship between them. But if you have three of them, you have a contribution from the intersection. From intersections of a singular things. Okay, so this is in a sense directly related to the first paper, where it introduces these notions. Except this is not written in there yet. Now, so the second paper which we have, it says that X is smoothable. So in C, symplectic variety X omega is smoothable. So smoothable means there's this Z omega Z over C such that such as the central fiber is X omega. So what you have is deformation. If and only if C1 of the fixed locus is 0. Now, so Gumpf stuff is what it says in the n equals 2 case. So non-central fiber of this this is n-fold version of Gumpf's construction. This is precisely what Gromov wanted. Except he wanted in a maybe without deformations, but one way it makes sense is deformation. And so the thing is, so this is what is called the triple point condition in algebraic geometry. And so it's necessary, but not sufficient in AG, even if n is 2. No, it's never. So the fifth one is x omega is so we have a symplectic manifold. So in this case, it's a smooth manifold. So we have compatible Hamiltonian actions by trace 0 subtori in S1 to the n. So by trace 0, I mean if you look at the diagonal, so product of the traces should be 0. So on some open U alpha inside of X, what this produces is produces x omega I symplectic manifolds and normal crossing variety and a degeneration to NC variety X, which is the union of these things.
This X is, you used X there.
So, okay. Context 0. Now, so the trace 0 subtori, if you take n equals to 2, there is only one trace 0 subtori. This is SI. S1 inside of S1, there's only one of them. It's the anti-diagonal. Now, and then this is standard. This is Lerman's symplectic cut. So when you look at Lerman's symplectic cut, he does not actually produce degeneration. He only produces two symplectic manifolds. So even in that case, we actually have more of a construction. And in some sense, this is inverse of 4. I mean, so as far as I know, there's actually no paper which says that Lerman's cut is the inverse of what proves that Lerman's cut is the inverse of Gauss symplectic sum. I mean, it looks very believable, but one actually has to make the precise statement of what this actually means. Incorrect sense. So one thing to remember that you cannot just say this right away. You cannot just say that the two things are inverses, because GAMP's symplectic sum depends on the choice of the trivialization of a line bundle. So there's a lot more structure. So, but this is still to be written, actually. I mean, it's still being written. Okay, so at this point, I don't actually have time to say about the proof, but the point, the way we actually prove the main theorem. So I really want to sort of focus on the big picture. And so the point here is that we have to deform, we locally have to deform forms to each other. And if you take two different symplectic forms, you have to be able to deform one into another so that the deformation is compactly supported around 0. And deforming forms to each other is easy, keeping them symplectic and close at the non-degenerate and close at the same time is more difficult. And then you have to place these deformations together. So there's some kind of induction on the depth of the structure in all this. Right, thank you.